Thank you so much for being here, everyone. Welcome to the released item analysis for the New York Earth and Space Science Test. I'm excited to introduce myself so you know who is talking to you. My name is Brendan Finch. My pronouns are he, him. You can tweet at me at birdbrainfinch. I taught middle and high school science. Earth science is one of the topics that I taught in the high school level for a virtual high school, which I tried for 1 year, and then went back to the classroom because that was awesome. I left the classroom, though, full-time in 2014 to build rocketlit.com. It's an adaptive science reading website, and it's mostly for middle school students. It's kind of my love letter to the students that I taught. And in the last 5 years, we have been working on inner orbit, which is the topic of our webinar today. And we're focused around NGSS, or we support a lot of schools and districts in New York State as well, assessments. And everything that Brian wrote in the chat is a big piece of this. I wrote a lot of the assessments on the site to start with, and now I spend a lot of time speaking with thought leaders to better support our admin, our students, and our teachers. There are some cool experimental things that we're building, and I'm excited to talk about that. And here's my little geology joke. It's difficult to smell what the rock is cooking, and that's going to come full circle in a little bit. Anyway, so what is inner orbit? Really, really quick, I want to introduce what we do. So inner orbit's pretty simple. So we find phenomena. So those are things that happen in the natural world that can be explained with science knowledge. And so we'll find things for Earth, life, and space science. Earth, life, and physical science. There's also space with the Earth. And each of those things we find phenomena that hit standards from the 3rd grade all the way up to the 12th grade. So we have all of those different grade levels in the site. And with those phenomena, we ask students really carefully scaffolded questions. So we want to ask them questions, not just at the level of proficiency, but finding ways that we can scaffold up those questions to get them up to the point where they are being successful. And as they're progressing, we want to give you really, really detailed data. So we don't just want to tell you that students understand developing using models, or they're struggling with analyzing interpreting data. We want to say that, and what we're looking at right here is one of our reports. We want to say that at the 6th, 8th grade level, the thing that students struggled with the most is they struggled with the ability to develop a model to describe unobservable mechanisms. And we have some data, and this is at the 6th, 8th grade level. And then we have some data that at the 3, 5 grade level, that's what's up top here, students were most successful using a model to test cause and effect relationships or interactions concerning the functioning of a natural design system. So the idea is that as you go through and have conversations with your colleagues around these standards, that you have really, really, really specific pieces of information that you're building, and you make sure that as you're talking to each other that you understand what your students need to do and where they're being successful. And that's kind of it. That's all we're doing. Okay, cool. And let me see if I can clear out those annotations. Clear all drawings. Yay. All right, cool. We'll close this. We don't have that. All right, great. Well, y'all, the last thing that we do, and this is something that I know 2 people in the audience also do a lot of, is we do a lot of professional learning. So I think the greatest lift that we found, if you're in this boat, then that's cool. You're there with a lot of people. That just understanding the NGSS, understanding sense making is a struggle. And so we spend a lot of time training leaders and training teachers on what it looks like to assess the NGSS and what sense making is. And so this is my colleague Erin going in person this is in Norwalk, Connecticut. And we also do a lot of virtual PD sessions, this being one of those. So welcome. If you would like to check out Inner Orbit and you'd like to try the site out, then you're welcome to find a time on our calendar. If you're watching this as a recording, it's going to be in the description. You can find a time on our calendar, or you can dive into the site on your own and explore our Earth science. And we also have life and physical science assessments as well. But without further ado, let's jump into our session for today. So today we're here to talk about the New York Earth and Space Science released item and do some analysis of that. The objective is to provide context for the upcoming, Earth and Space Science New York Science Test, the reviewing sense making. It's going to be a big part of what we do, and then analyzing some released test items. We did one of these for bio before, and we went a little bit under the hour. And so I think that's what we're going to do here as well. We're going to start out with the sense making intro. If you don't understand sense making, the rest of this is not going to make much sense. We'll talk about what the difference is between 2 different test items, and then kind of go into what are 3D standards. And then we'll talk a little bit about translating standards into assessments. And so that's going to involve looking at an actual performance expectation. That's what the standards mean. Then we'll look at evidence statements, which are really, really useful tools. And then y'all New York built some really amazing tools, which are PLDs, or performance level descriptions. And so we're going to dive into one of those for a standard in high school earth science. Now we'll talk at the end about calibrating assessments with PLDs. I think that the performance level descriptions give you really detailed, guidance for, is the level of questioning that I'm asking my students actually what they need to be doing? Or am I asking things that are far, far, far too simple? So we'll talk about what is proficiency first, because that's a good thing to know. And then we'll play what PLD level is this? And we'll look at some items and say, this is this item or that item. And then finally, we'll go through using some phenomena thread units. So I'm going to dive into the InterOrbit website and talk a little bit more about how you can use phenomena throughout your units. So if you're not doing this right now, that's going to be really, really useful. You don't have to use InterOrbit to do this. You could use anything where you're finding phenomena, but we have a whole bunch of them, and that's what I do. So I want to show you that. And we'll be here for some Q&A. And I guess my only other question is, can you guys smell what the rock is cooking? All right, that's it. Joke's over. Okay, so let's dive into sense making and talk a little bit more about what sense making looks like. And we're going to do that through the lens of two different assessment items. We're going to go through a Regents 2024 released Earth Science item, and then we're going to look at a 2024 the Earth and Space Science. So this is the NIST standards, not the Regents, but the newer standards items. And so I want you to consider these two different questions, and I want you to, in the chat, I'll ask a very, very clear prompt later, but I'd like you to respond and tell me a little bit more about what you're seeing in these two items, and really the differences between them is the big thing. All right, so a question I pulled from the released items for this year for the Regents: why is volcanic ash a good geologic time marker? So students have these different responses to look at, ash and volcanoes and geologic time. So they have to choose an answer for this. Okay, and then we're going to look at 2024. So if you don't know, there are small clusters of questions on the ESS release test items. So I picked one on the Juan de Fuca Ridge model. And so this gives some details about the fact that, we can track the changes in Earth's magnetic field, because we'll actually see these, different lines, this evidence of this in minerals, in rock layers on the surface of the Earth, which is kind of interesting. So there's a model for this, and then there's some information that's given to students, and the question is asked along with this. There's a couple questions in this cluster, but this is one. It says, describe how the pattern of magnetic field reversal of ocean floor basalt shown in the rocks on either side of the Juan de Fuca Ridge is evidence for convection currents in the mantle. What is the difference in what these two questions are asking students to do? And if you're watching this as a recording, you can write those in the comments as well, because we'd love to be able to respond to that. What's the difference in what these two questions are asking students to do? Question one from the Regents, question two from the NIST. The first question is really just a memorization question. You either know how volcanic ash can be used as a geologic time marker, or you don't. Question number two, the new release test item, students have to understand that there are changes in the Earth's magnetic field, or that there is evidence of those changes. They also have to understand that there are convection currents in the mantle, and that those convection currents may influence, some of the things that they're seeing on Earth's surface. And so this is really looking at differences in how systems internal are affecting external systems, or the elements of the surface of the Earth. And so for this question, students have to analyze data from the image that was given, and they have to cite that as evidence to explain how the convection currents in the mantle are evidence for the pattern of magnetic field reversal of ocean floor basalt. This is a really, really complicated question. And so the differences between these questions, I also want to give a more simplified explanation. And I think that they can be referred to as either representation questions or as sense-making questions. And so representation questions are kind of what the Regents is looking at. So it's communicating an idea that students have previously learned. Volcanic ash is this. That's how we can use it to show geologic time or track geologic time. It's great. We should know that students know things. If we don't know that students don't know things, that can be a little rocky. So diagnostic assessments, formative assessments, do you have this prior knowledge? Do you understand this thing that I talked to you about today? Those are really, really important. However, it is insufficient evidence of proficiency. Just asking students if they can explain some, basic elements of convection currents or explain what's happening with the changing magnetic fields. It's not making sense of something, and it's not what the standards are asking students to do. And frankly, it's not what your test is going to ask students to do either. And so those are all things to take into consideration. So sense-making questions, that's what that second question is going to be explaining why or how. And it's going to be making sense of something brand new. So if students are in your assessments, if they are looking at things that they've already seen and they're answering questions about things that they already know, then those are not sense-making questions. Those are going to be more representative questions, more Regents-like questions, even if it's a phenomena-based question, but they're familiar with the phenomena. Those are going to be things that are not going to be, it's not going to be sense-making. It's not going to align with what they have to do on the new standards. That's tough. This is ideal for summative assessment. If you give students novel phenomena when they are just kind of understanding the concept, it's going to be a little rough. So I strongly recommend that you give them these as summative assessments. And by giving them a novel phenomena, and by asking questions to explain why or how something is happening with that novel phenomena, it's a demonstration of mastery of the standard. It's the goal of the NGSS or the NIST list standards. And that is what we need to push students towards. All right. So now let's talk a little bit more about what these three-dimensional standards are. If you're super familiar with this will be very affirming, and you'll be like, yes, I know all of those things. And then we're going to get into a little bit more detail on not just what three-dimensional standards are, but how those translate into assessments. But understanding these standards is really important because the rest of this will not make any sense if you don't understand these things. So below, I have the 3 dimensions of the performance expectation that we're looking at there. It's HSESS 22. And you may see the standards represented in this little, I'm not sure, it's ribbons or something. And what this is showing is the 3 different dimensions to these standards. And we think of these standards as 3-dimensional. What this image means is that so one of the dimensions of the standards is the content or the disciplinary core ideas, or you'll hear those referred to as DCIs. This is what students know. So students know this thing about that there are convection currents and they drive plate motions. That there's volcanic ash, and volcanic ash can be evidence of geologic time because there will be layers where volcanoes have erupted, and we can use that to say like, oh, like this happens every couple centuries. So this is helpful. Or we'll see that layer across a wide area. We can say, oh, like it looks like this is all at the same time because that's when there was a big kaboom. So that's things that students know, which is important. Students have to know things in order to do the other things. So what students do with that knowledge are called the practices, or the SEPs, or the science and engineering practices. So for this standard, it is analyzing and interpreting data. And so students are not just expected to understand things about Earth's materials and systems, but they actually have to use data in order to demonstrate that understanding. And it should be novel data. And that's a really, really important piece for an assessment. And then finally, for this standard, the 3rd dimension are the cross-cutting concepts, and this focuses around stability and change. And so this is all about feedback mechanisms. And when we dive into the standards later on, we're going to see that feedback, either negative or positive, can stabilize or destabilize the system. And that's an important piece of this standard. And you're going to see a lot of the questions that we look at are going to ask about feedback mechanisms, and that is fun. Cool. And the cross-cutting concepts, I like to think of as lenses that students use to analyze phenomena. So it's not a skill that we have. It's not a piece of content that we know, but we're just going to constantly look at things and say, are there feedback mechanisms at play in this system? And are those things negative or positive feedback? So students have to know what those things are. They should be able to identify those things. And then are we stabilizing or destabilizing systems with those feedback mechanisms? And those are really, really important pieces for students to understand and then apply across life science, physical science, and earth and space science. Cool. So all of those 3 things are baked into this thing at the top, which is the performance expectation. So this says, if students analyze geoscience data to make the claim that one change to Earth's surface can create feedbacks that cause changes to other Earth's systems. And so that is the PE that we're looking at here. And that incorporates that analyzing data, that Earth's materials, and that stability and change. Cool. So HSESS 22, again, involves that DCI of Earth's materials and weather and climate. It involves that SEP of analyzing and interpreting data. And then finally, that stability and change cross-cutting concept. And all of those things are pulled together in order to ask questions like this. Whether or not this is a 3-dimensional question is not important for these purposes, but these types of questions, these complicated questions where students are understanding, analyzing data, they're using their knowledge and applying that knowledge to make sense of that data. Those are what we're looking for students to do on our assessments, what we need to get them to practice for for the assessment that's coming up next year. It's going to be exciting. Cool. These are phenomenal questions that we want to ask our students and we need to prepare them for. So I guess the question is, like, how do we do that? So Achieve, which is the organization that wrote the NGSS standards along with state partners, they put out some guidelines for how you should think about assessment. And they had two different columns. This is one of the resources from the Task Annotation Project in Science. So I want you to think about these two different things. So assessments looking less like these things, and then we'll talk about what they should look more like in the future as well. So first off, your assessments should look less like where students represent exactly what they've already learned and experienced. I used to do this in my class where I'd have an exit slip and I'd teach students about, erosion, and then I would ask them questions at the end of class about erosion. And we'd literally look at the thing that we talked about in class and I put that image back up on the board and I'd say, can you explain this image? Students would try to do it in the exit slip and that would say, I was successful or not. So that is no longer evidence of proficiency. It is evidence of progress, but it's not proficiency. We also want to make sure that students are explaining a phenomena or addressing a problem, that they're not doing something that they fully understand. So in my example of my exit slip, I say we're going to talk about, this very specific erosive force that we're looking at. Maybe, so I live in California and there's some mountains around us. Maybe we're looking at, mudslides or something like that. And there's always some like crazy mudslide that happens when it rains a lot. And so we could use that example. And I would have to use a novel example that is not a California mudslide in order to give students a novel phenomena. And that's not what we're seeing in the older items. And then we also have to make sure they're not just providing a factually correct or incorrect answer. There needs to be interpretation. Maybe there are lots of different pieces of evidence that you could pull from in order to say that this is correct or not correct. And it shouldn't be something that they've memorized. And I think that's what this factually correct or incorrect is all about. Instead, we want students to do more things like connect what they've learned and experienced in a new way. So they need to see something that is new. Those new things should be phenomena or problems that are where students are authentically uncertain. And so they shouldn't know the answer. They should have to kind of like grapple with their uncertainty in order to, connect the dots between what they know in class, what they learn in class, and to this new thing that they've never seen before. And they also need to make their thinking, including evidence-based reasoning, visible. And typically, we're going to see that through models, explanations, arguments, investigation plans, questions, and our predictions. All of those are SCPs if you are not super familiar. And those are all ways that we can demonstrate that students can, explain what they're thinking. We really want them to make sense and to show how they thought about those things. So not every single item needs to look like all of these things, but we want them to look more like the things on the right and less like the things on the left. And as long as you're making progress on that, then you are moving in the right direction. And that is what I want that's what I want y'all to do. Okay, now let's talk about translating those standards into assessments. And I think that this is a thing that is fairly esoteric, and I want to try to break it down a little bit more so that when you look at your questions, you can say, have I properly translated these standards into an assessment? Or am I just using something that I've been using for the last 20 years or 10 years or 2 years or whatever it is? And do I need to make some changes to that? So let's use this as kind of a litmus test for that. So first off, the performance expectations are the place to start. This is, it's not super simple, but is the simplest way to look at these standards and translate them into assessments. And so this involves, we need to make sure that our assessment items, we're preparing students to analyze and interpret data. So we're giving them data to look at. If there's no data there, probably not going to work out too well. And then the DCIs are the knowledge, that's the pieces they need. So if we're not asking about Earth's materials and systems, and if we're not asking about weather and climate, then these are going to be tough questions for students to really grapple with. And then finally, so the stability and change is the cross-cutting concept. So ideally, questions will also involve feedback mechanisms, and students will have to comment on those feedback mechanisms in order to answer those questions. So this is one, kind of the starting point for the rest of our, turning standards into assessments. And the second resource I want to talk about are the evidence statements. So these are great resources for kind of understanding what that whole big, hairy performance expectation and clarification statement means. So these go into great detail. This is the first part. There are two different parts of the evidence statements. I'm going to kind of give you a summary of these so it's a little bit more clear. So first off, students need to organize data. So for this standard, they need to organize that data to show changes in the hydrosphere, cryosphere, atmosphere, biosphere, geosphere. Explain how those changes, how those sphere changes affect Earth's surface. And students should describe what data sets represent. So in the beginning, as they're progressing towards their final performance, these are things they need to do. And they also have to identify relationships. So everything that we talked about earlier are just organizing things and identifying things. Now we're identifying relationships. So kind of how two pieces are connected. They need to analyze that data and describe those relationships. That changes in one system affect changes in another, and maybe that there are feedbacks to the climate. So this standard is really interesting because there is kind of like a sidecar to the standard, which is talking about human impact and climate changes. And so a lot of the assessments that we run on Inner Orbit focus around those things. But this item that we're looking at from New York State doesn't focus around climate changes so much as just those PEs. Yep. And so as was written in the comment, so there are no evidence statements that New York added to the NIST list. Cool. And so aside from just organizing data and identifying relationships, we want students to, and this is another kind of like sidecar to the standard, analyze data to identify effects of human activity. So super, super important there. Finally, at the end of their performance, students should be interpreting data. So they need to be taking that data, they need to identify relationships, they need to interpret it. And so for this standard, they need to use that data to describe a mechanism for the feedback. It could be positive or negative, stabilizing or destabilizing. And they need to use the analyzed data to describe a particular unanticipated or unintended effect due to human activity. And this is kind of like the sidecar to the standard, which is this kind of a human activity and weather and climate piece. And this is the evidence statements for this. This is not the New York standard. These are the evidence statements. But reading the New York standards are going to be the most important thing for y'all. And I'll get into the PLDs in a second, which are the blueprints for the assessment. And then finally, so we want to include a statement regarding how variation or uncertainty in the data may affect the interpretation of the data. So this is a really, really interesting piece to this, is that we always want to understand that there are biases in our data and be frank about those biases if that exists. I think this is really specifically referring to like the climate data, where you're looking at one thing and maybe there's a scale issue or a single variable issue, and many things that affect Earth systems are multivariate. And so we want to acknowledge that we're just looking at one piece of this and there are a lot of different pieces. That's important. Cool. The PLDs are the next thing that we want to go over. And this is probably the most important piece and concrete piece for folks in New York State. And so first off, how were these things created? So the PLDs, they essentially, so New York State asked, what claim do we want to make about what students can do? Because the performance expectations are all about doing things, performances of things. The end performance is where they started. So they took their performance expectation and they broke that down into different performances, just like that final performance expectation. But the PEs the performance expectations are something that we want students to understand at the end. And the problem, I think, the most difficult part with the performance expectations is there are a lot of little steps to get there. And so what the PLDs did is they show what those little steps might look like. And now questions are being written to those things. So important to know. We also want to know, what evidence do we need to see? So what is some evidence that we want to see from students? What do they need to do in order to show that they're making progress? And the PLDs are that progression of evidence up to proficiency. So what are different pieces of evidence we could use to do that? And then those PLDs are then used to design those questions to elicit evidence of proficiency. So this right here is the PLD for HSES22, where students are asked to do a lot of different things. So the high school PLDs, and if you're familiar with them, they have 5 different levels. They're different than the middle school and the elementary school. So intermediate and elementary PLDs only have 4 different levels. The high school ones have 5 levels. And what I'm going to do before we go too far is I'm going to strike out level 5. So we're not going to worry about beyond proficiency. We're not going to worry about exceptional performance right now. We're going to focus instead on that progressive performance, because that's what we want students to do right now. We want them to progress slowly from understanding things to being able to make sense of novel phenomena. So I'm not going to read out all these different levels, but I'm going to give you some summary statements on the level 1, 2, 3, and 4. So the level 1 question asks students to use geoscience data / information and identify one change in Earth's surface or an Earth system and how it will result in a change to another Earth system. So they just need to identify a change. So obviously, there are certain types of questions we can ask where students are just identifying a change. So that's level 1, which is emerging understanding. Now, level 2, which is progressing, is identify the information or provide evidence. So they can either identify the information or provide evidence that a change in one system will impact another system. Now, this is progressing towards this, and level 3 is the nearly proficient. So this is almost there. So for level 3, students have to analyze data or information to support a claim about feedback. So that's really, really important here. It has to be feedback that causes change to one or more Earth systems. They need to be analyzing data or information. They're not just identifying things. They're not identifying, the information or identifying a change. They're not analyzing that data. So there needs to be something more that they're doing rather than just pointing to something and saying that's the thing. And then finally, for proficiency, students actually have to analyze data to support a claim about feedbacks. There is a plural, which is really important. And instead of saying data/information, the data needs to be, I'm going to assume that this is going to be in some kind of a graphical or model form. So that data, it's not just data or information, it's data, and it's probably can be messy data. We're probably looking at multiple different data sets here, or a very complex data set that shows us, that gives evidence for students to make a claim about feedbacks that cause changes to Earth systems. So there are multiple different things. If you were here for the bio session that we did last week, it focused around identifying various, there was one of the level 4 involved models of things or data sets. And so the same thing, oftentimes the level 4, you're going to find much more complicated data sets that are the basis of that proficiency. And level 3 and level 2 and level 1 are going to have either singular data sets that you're looking at, or there isn't really data. Students are just identifying information or evidence, or identifying changes that are happening there. Great. So what I love about the PLDs is that they allow you to look at your questions and then to say, am I asking questions to identify that there are changes? Am I asking them to identify information or provide evidence? Am I having them analyze data and information? Do they really have to grapple with something new? And that's the only thing once they're analyzing that, where they're progressing towards proficiency. And then if I'm asking questions about proficiency, they need to be analyzing data to support a claim about feedbacks that cause changes to Earth systems. So we should be looking at multiple different feedback mechanisms and multiple different changes to those Earth systems. All right, great. So now onwards. Let's talk about calibrating assessments with those PLDs. And so when we're looking at those PLDs, and for this image, I have removed the level 5, because right now that level 4 is what's most important. And that level 4 is going to be the performance expectation. So you're going to see analyzed geoscience data to make the claim that one change to Earth's surface can create feedbacks that cause changes to Earth systems. And you're going to see that same thing on the performance expectation. So I just took a screenshot of the PLD and the PE, and they're the same. These two pictures are the same. And so when you're asking questions, you can look at that PE, use the NIST list ones, or you can look at the PLD, and those will both be the same thing for your level 4. And that's important to note that in that level 4, so students have to understand feedback, so stability and change feedback systems. They need to identify, that Earth's materials and Earth systems are dynamic, and also that the foundation of those things is radiation from the sun, and there's weather and climate changes as well. And all of these things have to result from analyzing data. So students have to look at data sets that can be, so it says very specific here, so mathematical things, models, technologies, and they need to be able to make claims from that data. That's the science and engineering practice piece of this. Okay, cool. So if we're looking at these PLDs and we're looking at all of these 3 dimensions that are kind of baked into each one of these things, now let's look at some released test items and figure out what PLD level is this question written to. So I'd love for you in the chat to write down what PLD level you think this question is written to. So we're going to use that same question that we had earlier, which is, why is volcanic ash a good geologic time marker? And so I want you to use the information here, and this is, I actually had trouble finding an item that was aligned to this PLD from the Regents test. It was difficult, but let's use this item, figure out where does this fall within the PLDs. Is this going to be closer to a level 1 PLD, a 2, a 3, or a 4? All right, so I see a response that says 0, which is not one of these things, but I think that the message here, just to be really clear about this, is that the old Regents questions don't even fall on the PLD scale. So these old questions are not asking students to even identify a change. They just have to know things, which is below the level of the performance level descriptions completely. Maybe it could be a 1 to say you're identifying a change or something like that, like by showing that There are ash deposits. We can see, like layers in Earth's surface, but it's not, I think that the message that I want to portray here is that in no way are students using those questions. And if you're asking questions like that, you're not preparing them to be able to, demonstrate proficiency on these things. And so if you ask questions like these old Regents questions for the new test, you should expect students to genuinely struggle on answering those questions. But if you prepare them with these other questions that we're going to go through, now you're preparing them and setting them up for success. So let's talk about some of those questions here. So second question, we're going to look at the new release test item. And so this question says, describe how the pattern of magnetic field reversal of ocean floor basalt shown in the rocks on either side of the Juan de Fuca Ridge is evidence for convection currents in the mantle. So this question that we're looking at here, and this is for HSESS 2-3, where students have to either say, given a model, identify evidence that shows the cycling of matter by thermal convection, or given a model with evidence, identify a stage of recycling of Earth's materials. So those are the two different pieces for level 1. Level 2, they need to identify evidence that shows the cycling of matter by thermal convection, or given a model with evidence, identify stages of the recycling of Earth's materials, or identify a rock or material using evidence to show the physical and chemical properties of rocks. This is definitely a rock cycle question. Level 3 is going to say, given a model, describe the cycling of matter. So here we have identify the evidence that shows the cycling of matter. And for level 3, they need to describe the cycling of matter by thermal convection. Or, given a model with evidence, describe the stages of recycling of Earth's materials, or identify the location of the formation of rock types using evidence from a given model. And then for level 4, they need to develop a model based on evidence to show what is happening here. Describe how the pattern of magnetic field reversal of ocean floor basalt shown in the rocks on either side of the Juan de Fuca Ridge is evidence for convection currents in the mantle. So evidence for convection currents in the mantle. We'll dive back over to that PLD for a second. So they're using that model to show how the basalt deposition is evidence of convection currents in the mantle. So what level is that question? So see in the chat that the word describe is within that question, which makes a lot of sense. So this might be level 3. You have to describe the cycling of matter, or are they just identifying evidence by describing that? The question again is, describe how the pattern of magnetic field reversal on either side of the Juan de Fuca Ridge is evidence for convection currents in the mantle. Though it says describe, I see them just identifying evidence. I think that this question, so that we're looking at for the release test items, is likely somewhere between a 2 or a 3. I think it depends on whether they're just citing evidence or they're describing the evidence. So if they're describing it, then that might work. But I think that this may actually be, it could be identifying evidence as well, which is really interesting. I can see how it can be a free response question or a multiple choice question between those two. Interesting. All right, great. So we're going to flip back to that performance expectation that we were looking at earlier in our session, which is HSESS 2.2. And so bear with me here. We're going to go back to, and we're going to look at an inner orbit item and figure out what level of the PLD that is. So we took a brief little detour to look at HSESS 2.3. Now we're back to HSESS 2.2. So this item says, based on the data provided, it's evident, and we give students a whole bunch of different data sets, and I'll show you what that looks like in a second. Actually, let's look at that now. So we give them these data sets. This is all about how can ice keep our planet cozy. Data sets on Arctic temperatures, looking at sea ice versus absorbed solar radiation, and then changes in air temperature and sea ice extent. These are beautiful images, super beautiful, from Zach Lape. Really, really awesome stuff, and also from NASA. And so these are a few different data sets that we give students for this phenomena. And we ask students this question. We say, based on the data provided, it's evident that the Arctic region is experiencing an accelerated ice melt due to rising temperatures. How could this phenomena potentially contribute to a destabilizing feedback loop? So let's take a look at our PLD levels here and figure out, this is one of the items from the in-orbit bank. What level is this item at? Are students identifying a change? Are they identifying the data that provides evidence for a claim? Are they analyzing that to support a claim? Or are they analyzing data to make a claim? So if this is PLD level 4, I just want to state that if this is a free response question, I think that it would definitely be PLD level 4. And so we'd see students would have to actually make a claim. I do think it my thoughts were that this was a PLD level 3, where they're analyzing geoscience data to support a claim. So they're choosing one of the responses below to help support this claim that, that there is some change. So like ice melt releases fresh water into the oceans, disrupting currents, which can lead to increased warming in certain regions of the globe. So in my mind, this is a PLD level 3, but I'd be interested in any evidence for a PLD level 4 because it's a multiple choice item, and that's why. Okay. Yep. So in order, from my perspective, in order to meet the level 4s on almost all of the PLDs that I've looked at, and I've looked at most of them, but not every single one in great detail, that students need to actually make a claim. They need to construct a response. They need to construct a model. They need to be drawing some analytical information, typically in a constructed response format. And so if they're not constructing a response on their own, they're not going to be at a level 4. And many multiple choice questions, though it's possible to write some that are complex enough to hit the level 3, many of those are going to be at a lower level. And so they'll be approaching. Yep, exactly. So I think constructed response is going to be a 4. It doesn't, so you could do constructed responses that are level 2s. You could do a level 1 constructed response. Just the constructed response does not mean that it's at a level 4. But yeah, we give them these, well, they have to identify or supporting the claim. And so you could make the argument for this that students are being given a claim as well. So say more about that. I'd be super curious to hear if there are other thoughts in the chat about that. And if you're responding in the chat, make sure that you're responding to everyone and not just to hosts and panelists. We have some smart comments coming in just to me that says the claim is provided actually, right? So the claim is one of the answers. It's not provided to them. All right, we'll let this rest. Think about it a little bit more. The point that I wanted to make with this slide is that if you want to, and some of these messages coming straight to me. The point I want to make with this slide was that if you want students to be meeting a PLD level 4, you need to have constructed responses. And you can have really complicated multiple choice questions, but they will never reach the level of proficiency that you need for students to be at in order to show proficiency on the PLD level 4. So for the Earth Science test, you need to be at PLD level 4 in order to do that. Okay, great. Thank you all so much for walking through that with me. And now let's talk about using phenomena throughout a unit. We find a lot of our teachers that we work with think about phenomena as an anchor phenomena, and then they think about them as assessment phenomena. Hopefully you have a phenomena you're using as your anchor phenomena, which students slowly peel back the layers on and make more sense of throughout the course of a unit. And then you have phenomena that are separate from that you are giving them as a way to apply their understanding of the anchor phenomena to something new. Because on the science test, they will have to apply what they understood from your class to something new. And so giving them practice for that is important. So you can give them a single, at bat as a summative assessment, but in my opinion, giving multiple different phenomena throughout a unit is really, really helpful. So we're going to go back to this HS-ESS 2.2, where students analyze geoscience data to make the claim that one change to Earth's surface can create feedbacks that cause changes to other Earth systems. And we're going to look at ways that we can use phenomena throughout a unit in a roadmap. And so first off, at the beginning of a unit, we can either use an anchor phenomena, or after we introduce that, we can give students a separate phenomena for a lesson. And I, as the teacher, can walk through the data sets, I can walk through the models, I can walk through the investigations, whatever it is that I'm giving students, and I can talk about it. I can model the process of making sense of this phenomena. And then maybe in the middle of the unit, we can give different groups of students printed assessments. So I know that there's, we're not sure what that high school assessment is going to look like, whether it's going to be computer-based or not, but we can give them different printed phenomena, printed assessments, or you can do this on a computer as well, but have students work in groups and try to answer questions about that phenomena to try to make sense of it. So they've gone through some instruction, they should be able to answer some of these questions. And then finally, at the end of the unit, we want to give students an individual assessment using another phenomena. So ideally, each of these are separate phenomena. And if you go onto the InterOrbit website, you do not have to use InterOrbit, and you search for something like HS-ESS 2.2. So we have 5 different phenomena for this. So you could give lots more phenomena than what was just mentioned, but you can allow students to look at, what fed Canada's firiest year, and dig into some data sets about wildfires and look at the CO2 concentration, across these different years and ask questions about that. We can look at how can ice keep our planet cozy. And then we can also say, how can positive feedback have a negative impact. And this looks at increasing CO2 and that impact on water vapor, and looking at different ways to mitigate atmospheric carbon removal. So either tree restoration, air capture, carbon mineralization. So this is very much an engineering concept. And then this is looking at coral reefs, losing their color. So there's lots of different ways that we can take the concepts of these different feedback mechanisms and then apply those to changes in Earth systems. So all of these are great phenomena to use as your, on grade level content. But let's say your students aren't ready for that on grade level content, or you gave them assessments and you're like, yikes, like they are not ready for that. So we can go back from that high school standard and go back to the 2 middle school standards that lead up to that. And I think that, we find a lot of high school teachers really want to teach at the level of rigor of the high school content, which is wonderful. But if students are not ready to grapple with the SEPs at the high school level, then go back and give them opportunities that are highly scaffolded and that are more accessible for them from middle school. So that there are 2 PEs that lead up into that high school HS ESS 2.2. There's MS ESS 2.1 and MS ESS 2.6. So 2 different standards for middle school that are articulating up into that high school standard. And so what we can do is we can walk backwards from that standard and we can ask questions from our middle school areas, and we can dive into, so on an orbit, if you type in MS ESS 2.1, you're going to have several different phenomena that you can pull from, and you can ask students questions about Earth's processes. And just this is really kind of like a rock cycle standard. And so we can just ask them questions about the rock cycle and ask them to dive into much more simple data sets and images to explain what's happening in the rock cycle and how Earth's materials change over time. And in addition, there's MS ESS 2.6, so you can dive into standards or phenomena for MS ESS 2.6 and ask them to explain why are these sites the best for flying kites, or how does the motion of the ocean affect the heat on the street, and how might monsoons make many muddy months. That is a tongue twister. And so all of these are just examples of different standards and different phenomena that we can use to give students ways to grapple with those earth science concepts that lead up to those high school standards. Great, cool. And so on in orbit, if you're not familiar with how we write our questions, they are not the same as the PLDs, but they are similar. We like to think of our questions in these different buckets. And so we first will write questions that are prior knowledge. So we'll take that high school standard and we'll go back a grade level to the middle school standards that articulate up. If you're a middle school teacher, we'll go back to the elementary standards, the 3-5 standards that articulate up into that. Sometimes there's a single standard that goes to that high school standard. Sometimes there are multiple, like 2 or 3 different standards. So that's super important. After that, we ask questions that we call core content questions. They're DCI only questions. These are similar to the Regents questions, where it's you know a thing or you don't know a thing, but they're tied to the performance expectations, which is important. And then later on, we'll ask things about the content and the concepts, so the DCI and the cross-cutting concept, or the DCI and the practices, so the SEP. These questions allow us to gather data on whether students are struggling with that cause and effect, or stability and change, or structure and function, those cross-cutting concepts, or if it's the using mathematics or developing using models or constructing explanations. So those are all different question types we have on the site. And then we also go ask three-dimensional questions, which are going to approach the level of proficiency, or for our free response questions, will certainly be at the level of the performance expectation. That's what they are written to. Unlike the questions that we see on the New York State test, so we write our questions that are 3-dimensional with a rubric where you grade students on the DCI and the SEP and the cross-cutting concept independently. So instead of just giving them a score for all 3 dimensions together, we like to split that up into seeing how they performed at the DCI, the SEP, and the cross-cutting concept, and then all of that stuff goes into the reports. So you get lots of juicy data to check out. Awesome, cool. And that's it, y'all. Thanks for being with me. Thanks for joining me through this webinar. I hope this got things kind of bubbling around in your brain, like our little lava lamp friend here. Super fun to go through this with you. Thank you very much to folks in the chat for asking questions and interacting. It's really fun to learn a little bit more about what y'all are thinking about these standards and answer your questions. So I really appreciate it. And so I am gonna paste some links in the calendar if you want to find some time and chat with me about Inner Orbit. If you're watching this as a recording, you can check out one of those links in the description of the video. But otherwise, I hope y'all have a beautiful afternoon or evening, wherever you are, or morning if you're watching this recording. And thanks you all very much for being here and being a part of this. I hope the rest of you have a beautiful rest of your day. Thanks, everybody.